Hey everyone, welcome to gas chemistry. This is not a particularly difficult unit. In fact, I think it's probably the easiest. And gas chemistry is very much an application or an extension of what we did in 10th grade. And I'm going to start by just reminding you of pressure. And the reason why is because in terms of what we think of solids, liquids, and gases in generating pressure, gases by far dominate that conversation. Sure, you can certainly have pressure generated by flowing liquids. However, in this context of chemistry, it really does focus almost exclusively on gases. So there are two ways to change the pressure, um, by changing the force or by changing the area. And when we talk about gases and their response to changes in volume and temperature and moles, it all comes down to one of these two factors, force or area. As we increase the temperature of a gas, of course, um, which of these two factors do we change to increase the pressure? It's the force. So as we increase temperature, because temperature influences the kinetic energy, right? The 1/2 mv squared of a gas, where v is velocity. As we increase the temperature, we increase the velocity of the gas, and therefore it's going to hit the sides of the container with greater force. And because gases expand to fill the size of the container that they are in, the origin of pressure is the pounding of these molecules against the side of the container. Now, if we are to change not the temperature, but instead simply increase the number of gases or the mole of gases in a container, we are increasing the pressure not by increasing the force with which they hit the sides of the container, but the frequency. And so the additive force of additional moles of gas increases the pressure, not because they're hitting faster or harder, but because of more frequently. If in addition, so remember, moles are represented by N in gas chemistry. So as we increase the temperature, the pressure goes up. If we increase the moles of gas, the pressure goes up. And we have an opposite relationship. If this same number of moles of gas were in a container that's larger, and we increase the volume, the pressure goes down. So temperature up increases the kinetic energy, increases the pressure. The number of moles go up. There are more molecules hitting the sides of a container in a given area, the pressure goes up. If we increase the volume, the pressure goes down. So that's an indirect relationship. And as you probably recall, there are two gas laws. Now, PV equals nRT is called the ideal gas law. And we didn't really talk about why it's necessarily called ideal gas law last year, but we will this year, where P is the pressure in atmospheres, V is the volume in liters, N is the moles in moles, T is the temperature in Kelvin, right, which as we recall It's the degrees Celsius plus 273.15. And then R is called the universal gas constant, 0.0821 liters times atmospheres per mole K. And that's moles times K. Now, I do want to point out that we've talked about R before, not just in 10th grade, but also this year. And when we do equations that involve energy, we have what's also called the universal gas constant or the gas constant. And it has a different value. So whenever we're doing energy work, as we have previously this semester, we're talking about delta H, enthalpy, delta G, the change in free energy. That's where we have a different value of R, and that's 8.314 joules per mole K. Now, of course, the top is where they differ, right? Liters times atmospheres versus joules. And so when we're doing energy work involving joules, we use this value of R. And when we're doing gas work, we use this value of R. Now, it's very important. And if you forget the units of everything that it needs to be in, simply look at your formula sheet and then look at the units of the R value. You don't have to memorize this number. It's on the formula sheet you're given for the AP exam. And this tells you exactly which units everything needs to be in. So this is called the universal gas law, and that should be familiar to you. A rearrangement of the universal gas law is if P1 or PV equals nRT. If we rearrange this, we could rearrange this as PV divided by NT equals R. And what this tells us is that pressure and volume are inversely related. If the pressure goes up, the volume must go down at constant moles and temperature in order for R to be a constant. And you could sort of restate this relationship if it's P over T, if you're looking at these two, right, at constant volume and at constant moles, then it's a direct relationship. If P goes up, T goes up to maintain this constant of R. So another way of looking at this is P1 V1 over N1 T1 equals P2 V2 over N2 T2. So if this is called the ideal gas law on the left, this is called the combined gas law. And whereas this is extremely straightforward, plug and chug, as long as you have the right units, right? This is a scenario where you are given pressure, volume, moles, and you're asked to solve for temperature. Or you're given temperature, moles, and volume, and you're asked to solve for pressure. The main difference here is this is one set of conditions, right? You have three variables and you're solving for the fourth. Now, over here, we have a different scenario where this is before and this is after. And what this tells us is this isn't one set of conditions, but this is changing conditions. So you use either the one on the left, the ideal gas law, or the one on the right, the combined gas law, depending on your scenario. When you are given a scenario which states, excuse me, when you are given a scenario that states you have a balloon of helium, and you take this balloon of helium, which is outside, maybe in the room, and it's got a temperature at 22 degrees Celsius. What happens when you decide to do an experiment? And you take your balloon and you decide to put it inside of your freezer. And inside of your freezer, right, where it's, let's say, 4 degrees Celsius. How does the volume of the balloon change? Because the air pressure is going to stay the same, air pressure is not significantly different inside of your freezer. This is your refrigerator handle, by the way. Inside of your freezer, the air pressure is the same, and we're assuming that no moles of gas leak out. So the question, okay, asks us, what is changing? It is the temperature. What is staying constant? The pressure is staying constant, and the moles of gas are staying constant. So what we're asked actually is, if I have the initial temperature, right, of our gas, and let's say I'm told, right, that this is 4 liters in volume, by putting it inside the freezer and lowering the temperature, I could predict, if I know the temperature, right, at which it's going to, and I know the temperature at which it started, and I know its volume at this higher temperature, I can predict using this equation what the new volume would be. Now, unlike the previous ideal gas law, you can leave pressures, volumes, you can have those in milliliters or liters for volume, ATM or millimeters of mercury for pressure, because the conversions to ATM or liters actually cancel. The one thing you must remember is that when plugging into this equation, you cannot plug in Celsius, but you must plug in Kelvin. So in this scenario, this equation reduces to V1 over T1 equals V2 over T2. What I say is memorize P1 V1 over N1 T1 equals P2 V2 over N2 T2. And whenever you have changing conditions, always start with this master equation. And what you will be able to do is then figure out, the new norm, right? By canceling the, excuse me, the units that do not change. Another example might be a pressure and temperature. If you have instead a rigid container, right? This rigid container, let's say, is 10 liters. It's not going to change, it has hard walls. Now let's say you have a given number of moles of gas in both of these containers the same. If you take this container, right, and you heat it up to 40 degrees Celsius, and you take this container, right, and you heat it up to 90 degrees Celsius, you could either look at this in one of two ways. It could be the same container, or it could be two equivalent containers with the equivalent number of moles heated to different temperatures. Both cases, this works. And the question is, well, if the pressure in this first container, right, is 2.5 atmospheres, what will it be at this container, right? Question mark, what is the new pressure? So we start with our master equation and we cancel what does not change, right? V doesn't change and N doesn't change. So this reduces to P1 over T1 equals P2 over T2. We plug in, right, the initial pressure over the initial temperature converted to Kelvin, and then we solve. P2 is our unknown, and then we divide by T2, 90 degrees Celsius expressed in Kelvin. So whether you're using the ideal gas law or whether you're using this combined gas law, it's really very much plug and chug. A couple more things I want to point out before giving you some practice problems to try. So with this, right, PV equals nRT, one thing to note is that moles, in fact, can be easily converted from grams. And so you may have a problem where instead of the moles of gas, you're just told, I have 2.5, right, grams of neon. Well, in order to use Thivnert, we simply use the molar mass of neon to convert to moles. So there's something to be aware of. One more thing to be aware of is a substitution which we did not do in 10th grade. And this becomes really interesting and useful in a variety of different scenarios. So another way of expressing moles, right, or getting moles, is if you take a gram sample of whatever substance you have, right, and then if you divide that by the molar mass, right, you get the moles of that substance. So there is a substitution that is often done. What if instead of moles, right, N moles, I substitute this into the equation? And I'm going to call the molar mass a capital M. And it's often shown as a capital M in italics. So PV equals, instead of N, I'm going to have G for grams times R times T. And then this is, instead of grams per mole, right, divided by the molar mass. Now, I may be able to rearrange this equation. And in fact, we would have done this particular equation experiment to solve for the molar mass of a gas. And I'll show you what that would look like in a moment. But first, let's rearrange this. Let's rearrange and solve for the molar mass. So PV times the molar mass is equal to GRT. And then the molar mass is equal to GRT over PV, right? And these are all multiplied by one another, right? That's P times V. This is G times R times T. So this equation is a common rearrangement. And what this allows us to do is actually, if you have a gas, let's say it is a volatile gas like methanol, and I put some liquid methanol into a test tube, and I cover that test tube with some sort of, foil or parafilm, and I prick a tiny hole in it. And I heat this gas. If I heat it for a little while, I heat the liquid. So methanol is a liquid to start. If I heat it for a little bit, it turns into a gas. And so it vaporizes very easily. And what happens is some of that gas leaves. And the amount of gas that leaves at first is the amount of gas needed to equalize the pressure in and out of the tube. So if I then take this tube and quickly put it in a beaker of ice water, okay, that's cold water, and then I go, what happens is the gas liquefies quickly. And I can measure its grams. R is a constant. T is the temperature of the warmer gas when it was up here, okay? P is the room pressure because the gas inside the tube equaled the gas in the room pressure. And V is the volume of my test tube, right? Because the gas expanded. So if I use the original warmer temperature and I use the volume of my test tube, what I end up doing is having all of these, and I can figure out the molar mass of my gas. That is one experiment we would have done had we still been in school. One more thing. Sometimes this same equation is written one more different way. So if you have the molar mass of your gas times its mass times R times T divided by pressure times volume. One other way to express this is mass over volume is what property? Of course, it is density. So the molar mass is sometimes equal to the density times R times T over P. And so sometimes you'll see it like this, where instead of the mass of the gas divided by the volume that it's in, those two terms are combined into density. So here are some things to think about with our gas unit. And I'm going to now assign some problems, either follow-up problems or problems from the back of the textbook chapter to help you sort of process this, work with this a little bit. And then we're going to move forward into a couple other things such as, well, why is this called the, quote, ideal gas law? And what does it mean if the gas is not ideal? So we're going to look at a couple other things, but really, this is not that difficult compared to some of the crazy stuff we've done this year. So I hope that you take this opportunity to really sort of understand 100% the problems that we're doing, because I honestly think that every single person in the class could reach 100% with this particular level of content. And it's a real chance for you to sort of slam dunk that part of the AP exam. All right, so please send me an email if you have any questions. But now we're going to try a few practice problems in this arena.